Friends, welcome back to the course on quantum mechanics and the relativistic regime. In the last few lectures, 3 to 4 lectures, we have been looking at we have been reviewing quantum mechanics, and in the last lecture we looked at special theory of relativity. So we looked at what is the Einstein notation, what are the postulates of special theory of relativity. Of course, I assume that most of you will be having the relevant background in special theory of relativity, but this review is just to make uh, you remember those concepts essentially, and then just for completeness sake. So okay, and so these are the Lorentz transformations and the Galilean transformations, and we discussed all these concepts, and then we introduced the 4 vector notation or the Einstein notation of special theory of relativity in terms of vectors, scalars and tensors. How do you write invariant quantities, what are derivatives, how do you write derivatives, and so on, so essentially. Okay. And then so we introduced the examples of vectors, and then energy momentum tensor, the Lorentz transformations, and so on. So today we are now ready, because we have reviewed quantum mechanics as well as we have reviewed special theory of relativity. Today we are going to take the first step to have towards understanding of our first step to learn relativistic quantum mechanics. So in that particular sense, today is the first lecture on the topic of the lecture, this thing, after reviewing everything. So the first question we ask is, when are particles relativistic? When are particles relativistic, and when can you apply quantum mechanics for them essentially. Now let us take a system like a black hole at the center of the universe essentially. So you have a black hole at the center of our galaxy, so we have a black hole which is a very huge black hole essentially. So we have something like this, essentially a huge black hole. It is just a representative image, and there is some radiation around it essentially. So there is a black hole at the center of the galaxy, and then there are a lot of objects which are traveling around this object. So imagine that there is a star which is rotating around this black hole. Okay. This star around the black hole also travels at the speeds close to the velocity of this star, would be very close to the velocity of the light. So this object is relativistic essentially, because it is classically relativistic, but it is not quantum mechanical. This object is relativistic. There are some objects which have been discovered which have been traveling with 0.6 c, okay, 0.7 c. So there are several objects which are being discovered which travel very close to the speed of light, okay, within a few percentage. Now on all these objects, obviously we cannot apply quantum mechanical picture, because this object is a classical object. So this is a classical relativistic, okay, object, and you do not really can apply relativistic quantum mechanics here. Essentially it is a classical relativistic object. Now on the other hand, let us imagine a particle like an electron essentially. So we started with stars, and then go all the way to the smallest known object in the universe, essentially the smallest known particle in the universe. Okay. Okay. So, at the atomic level, so let us take a case of an electron. So, the electron, so right from somewhere around say several thousand hundreds of solar masses all the way down to an electron mass essentially. What is the mass of the electron? And yesterday we learned the natural units which convert everything in terms of energy units. In terms of energy units, we also considered that mass will be given in terms of GeV. The electron mass is about half an MeV, sorry, not a GeV. Okay. MeV is a million electron volt essentially. So, the electron mass is essentially 0.511, okay, 0.511 MeV. Now, if you want to really do convert back into kgs or whatever it is, you have to put actually a c square here essentially and then convert everything into masses and so on. So, okay. Okay. Now, but if you take c is equal to 1 natural units, so we just do not c is equal to 1 and so this just remains, okay, MeV. This rest remains as to be half an MeV. So, when the particles are of extremely high energies, in this case is electrons, the classical system, normally what is the energy of an electron? Essentially what you will say that what is the kinetic energy of the electron. So, the energy of the electron at the classical level is p square by 2m, this is classical. When I say here, this is not in the sense of classical, it is not relativistic, it is not relativistic. The energy formula, the kinetic energy formula in the relativistic case or you must be knowing in the C not equal to 1 regime, that is equal to p square c square plus m square c power 4, okay, but c is equal to 1 we write it as e square is equal to p square plus m square. This is the relativistic regime. Okay. So, the classical case is p square by 2m the energy momentum relation. In the non-relativistic in the relativistic regime, this just becomes p square by 2m essentially, p e square is equal to p square plus m square, okay, p square plus m square. Now, you can classify, now you can take the most general formula, okay, in the h cross and c is equal to 1 limits. Let us consider this e square is equal to p square plus m square. This is more general, okay, more general compared to what we typically write for the kinetic energy. Okay. For free electron, that means it is not bounded by any potential or something. So, we can write E square is equal to p square plus m e square. E square is the mass of the electron. Now, you can consider 3 different regimes, you can consider 3 different regimes. One, the momentum of the electron is much smaller compared to the mass of the electron, that is non-relativistic regime. Okay. When the momentum of the electron is comparable to the energy the mass of the electron, remember that momentum, so when c is equal to 1 and h cross is equal to 1, always remember h cross is equal to 1, c is equal to 1. Momentum, everything is measured in terms of GeV essentially, okay, everything has the same units as energy. Okay, everything has the same units of, as energy. So you can have p square much less than me square. This regime is non relativistic. This is a non relativistic regime. Now if you have p square comparable to me square, okay, this is a relativistic regime. Okay. Now you can have also a case in which p square is much larger than me square, so that you can completely neglect it. Okay. So let us say, okay, let me say double arrow me square. That means p square of the electron or the momentum of the energy, electron is so high that you can actually set the electron mass to 0. So this is the ultra relativistic regime. So whenever you have the momentum of the electron closer to its mass scale essentially, so or much larger than the its mass scale, in both these cases you need relativistic quantum mechanics. So what do you so you in these two cases you need relativistic quantum mechanics. Classical mechanics will fail essentially. Here you can use ordinary quantum mechanics, non relativistic quantum mechanics, or I will just call it as quantum mechanics. And this is what we revised the last few days essentially. Whereas in this particular case you need to have relativistic quantum mechanics, you need to have relativistic quantum mechanics. You can no longer use non relativistic quantum mechanics. Now you can have another scenario in which the momentum is okay. So the first scenario we are considering is when the particles have extremely high energy. In the then you can have systems, okay, B. So you can have systems in which, okay, systems with relativistic corrections. So systems with relativistic corrections. So this is like thinking that relativistic corrections to non relativistic processes. Okay, non relativistic systems, these systems are basically non relativistic, but you can have small tiny relativistic corrections essentially. So the finest example of this is one of the most important artifacts of relativistic quantum mechanics, which we will do a bit later. Okay, fine structure of hydrogen atom. In the hydrogen atom, the electron, okay, can reach relativistic energies essentially in the hydrogen atom. Okay. So, but these tiny relativistic energies the relativistic energies of the electron will lead to tiny corrections to the atomic spectrum, but this atomic spectrum is measured so well, so precisely, that these tiny corrections also will play a big role essentially. How do these tiny corrections come? So instead of the Schrodinger equation, if I start with E square is equal to p square by 2 m square, okay, and then I write E is equal to m into 1 plus p square by m square whole power 1 by root 2 square root of this. Now this, if I make an expansion, binomial expansion, 1 plus p square by 2 m square minus p power 4 by 8 m power 4 plus so on. plus so on. This piece is the relativistic correction essentially. This piece is the relativistic correction. So, it is not in, so the relativistic correction means that this piece is a tiny effect, but this tiny effect can be measurable. So, if the experiment is so precise, okay, so we are still in the non-relativistic regime, but the p power 4 by 8m cube term or 8m square term is not very tiny, it has some observable effect, and this observable effect can lead to a change in the meaning can be measured very precisely, okay, and this can be measured. Now, in the, we are talking about hydrogen atom, right, for example we were talking about hydrogen atom. In hydrogen atom what happens is the ground state, so the ground state of the hydrogen atom E0 is equal to minus 13.6 eV. This is, everybody knows this, which we have, okay. The correction delta E0 to the ground state is of the order of minus 9 into 10 power minus 4 eV. So, assuming electron mass is around half MeV, okay. So, you see this correction is very, very small, the correction is extremely small, it is 10,000 times smaller than the ground state energy. So, the average correction is around 10 power minus 3, if you want to say 9 is 9 into 10 power minus 4 is equal to 10 power minus 3, and then so it is 10,000 times smaller than the ground state energy essentially. Now, if you took the ratio of delta E0 by E0, so roughly around 10 power minus 4, but the experiments are extremely good, like I was telling. So, this the spectrum wavelengths, the spectral wavelengths of hydrogen are measured over large length scales, essentially large length scales. I will tell you length scales. In fact, there is relativistic correction comes out to be in hundreds of nanometers essentially. These wavelengths, the wavelengths due to these corrections, the wavelengths are in principal series series, okay, and they are about hundreds of nanometers. So, let us just take to be 10 Armstrong, that comes out to be, okay, 21 centimeter line, 21 centimeter line. Atomic hydrogen is everywhere abundant in galaxies, atomic hydrogen. So, it is present in the in gaseous states in most of the galaxies, okay, surrounding the galaxies, and I cannot so radio telescopes radio telescopes measure this 21 centimeter line, okay, measure this 21 centimeter line very precisely, and I cannot tell you the significance of measuring this 21 centimeter line to say for example it has on modern physics essentially. So, this is one of the first motivations or one of the first results what we are doing looking at is the reason why we should study relativistic quantum mechanics, because you have already one artifact essentially which tells you that that there is a an observable in the present universe which has significant effect on the physics we know. Okay. So, radio telescopes measure this one, and has significant impact on modern physics. Now, to give you one application of this 21 centimeter line. So, we all know that we can measure the virial velocities of the meaning the velocities of the stars circulating around the center of the galaxy. Now, these measurements are mostly done by measuring the 21 centimeter line essentially to guess what is the amount of mass, okay, what is the amount of mass inside the sphere where you are measuring this 21 centimeter line essentially. So, these measurements have such a significant impact that they led to the discovery of dark matter, and its related physics, So, all the physics related to dark matter and everything has been a significant effect of what do you call a significant impact came from the measurement of the 21 centimeter. It is not the only thing, but of course, but okay. These are extremely precise measurements, and again as I said relativistic quantum mechanics plays a very important role essentially. Other thing which we can think of is graphene. Graphene is a system in condensed matter systems, essentially material systems. They are specifically mentioned a class of systems in condensed matter physics, where particles obey relativistic. Now, I put quote unquote relativistic here, I will explain what it means. Relativistic dispersion relations. Okay, in condensed matter system, the system is actually non-relativistic. Okay, the system is already non-relativistic. Okay, so but they seem to be, it is not c, but it is not the velocity of light. Okay, but the particles seem to be obey something else other than the velocity of light, meaning the c is replaced by say some c tilde, say for example, but the dispersion relation will be roughly p square plus m square. So, the dispersion relation means that this is just the dispersion relation means that this energy momentum relation essentially in the medium, okay, in the medium, okay, in the material medium seems to be obeyed we seems to be obeying this E square is equal to P square plus M square. It's a which is a relativistic energy momentum relation, except that because it is inherently a non-relativistic system, here here the constant which appears which we call C tilde, say for example, is not the it is acts like the speed of light, but it is not the speed of light, is not the speed of light in vacuum. In vacuum. Okay. Now this is one thing. Now in fact it turns out that to be really in graphene what happens is they satisfy the Dirac equation. Which is an inherently relativistic system essentially. Okay. The half spin particles essentially and the fermions or spin half particles satisfy the Dirac equation in 2 dimensions. In 2 dimensions, we will see that in later on when we deal with how to do Dirac equation in 2 dimensions. So the system satisfies the Dirac, or the particles of the system satisfy the Dirac equation in 2 dimensions. So what we have seen is that studying relativistic quantum mechanics, and then okay, then there are Marano modes and so on. So there are a lot of systems in especially in 2D materials which exhibit phenomena which are explained by relativistic quantum mechanics, okay, the dispersion relations of relativistic quantum mechanics and like things like and Marano modes, Dirac equation and so on. So essentially, so what we have seen are 2 applications which make sense, which motivate, or rather than okay, which rather than make sense, which motivate us to study relativistic quantum mechanics, because there are 2 modern day applications which I can tell you that immediately we can they have applications both in condensed matter, other in astrophysics and particle physics and so on. So this is one subject which unifies both condensed matter physics as well as astroparticle physics essentially. Okay. So I will stop here and then I will start again on continue the discussion on relativistic particles essentially. Okay.